Hello, I am Zoe Straughn, and my partners are Gigi Schaefer and Luke Brothers, and our project is the impact reducing prosthetic liner with variable volume and integrated haptic feedback. So the focus for our project is transtibial amputees. Transtibial or below the knee amputation is a surgical procedure to remove the lower parts of the limb, in this case the foot, ankle joint, distal tibia, fibula, and the corresponding soft tissue structures. And then with nearly 2 million lower limb amputees in the world, with 50% of these being transtibial, our project does have a widely established customer base. So our background research has identified two key issues facing the transtibial community. The first is swelling and bruising due to high pressures and changing limb volume. The second is a widespread lack of proprioception research towards lower limb technology. And then these outlined key issues led us to identify these three needs: impact pressure reduction, real-time volume change, and a haptic feedback system. So here's our design overview, which has three main parts. The first is a haptic feedback system, which has three main components: the four sensors, the Bluetooth, and the nodes. The second is the impact reducing liner, which also has three main components: the oobleck, the lotion, and the distal end cap. And then thirdly is our variable volume system, which also has three components: the reservoirs, the sensors, and the exit route. We want to highlight the dynamic nature of our system compared to the competing technologies, as it can make real-time adjustments as compared to the static nature of current market products. So, getting into the haptic feedback aspect of our design, we have created a nano Arduino-based circuit to relate forces to changes in output voltage. This system places 5 force-sensitive resistors, or these circular discs, in parallel to receive a constant 5 volts from a battery-powered source. When the sensor is compressed, the resistance sees an increase we see an increase in the resistance, which causes a change in the output voltage. This change in output voltage can then be read by our analog pins, which is then transmitted into a data packet to our secondary circuit. Our secondary or actuator vibrational node circuit reads values coming from that Bluetooth module, parses through the data, and then these values are used to vibrate the nodes accordingly, with higher values matching higher levels of vibration on the residual limb. We then put these circuits into a 3D printed case, which can hang on the outside of the prosthetic socket. This does give it somewhat of a bulky fit, which is something we're hoping to miniaturize down the line. Now to look at our impact reducing liner. We started by creating a benchtop system. We used SolidWorks to allow us to 3D print the bones of the residual limb with an 80% infill, as we wanted it to be really tough. And then around the 3D printed bone, we simulated the muscles and tissues using EcoFlex, which gives us the closest physical properties of that residual limb for testing purposes. So then for our pressure testing system, we have this set up here. So our residual limb attaches to this base and then allows a non-amputee to place their leg here and then walk around and perform our testing. So for our pressure dynamic testing, after we developed the pressure sensor circuit, we wanted to determine where to place the sensors within the liner to cover the vital regions we needed. So on the left here, we have a color map that depicts the anatomy of the distal end of the residual limb. The areas here shaded in green are the pressure tolerant regions that can withstand higher pressures without discomfort, as opposed to these red areas, which are the pressure intolerant regions, which cannot withstand much pressure without pain. We place 2 sensors on each of these regions, lateral and medial for the pressure tolerant, and then distal and tibial crest for the pressure intolerant. So this is an example of what our pressure dynamic testing look like. Each of the peaks represents a step off the ground, and then each of the troughs are where the foot is then placed back on the ground. It is important to note here that all of the values never touch 0, which means our sensors always maintain good contact. So here are some of the results from our liner testing. These graphs show the minimum and maximum pressures for both our liner, here the prototype, and then the competing technologies for each of the sensor regions. Higher pressures here are bad, and we want to get lower pressures. And then here's the summary slide, which is going to show all of those previous pages of data in an alternative way. So this is looking at it by each sensor location. So as we can see, nylon sheaths here performed the worst across the board, having the highest levels of pressure. Again, we do not want high levels of pressure. Anywhere above 100 psi is going to cause physical damage to the limb, so we definitely want to keep it below that. So And then the socket was the next on the list, performing the second worst. And then the silicone liner was a close second, but it did fall short in impact reduction as it was worse than our prototype overall. And then, as you can see, our prototype performs the best, having the lowest pressures in 3 out of the 4 sensor regions. And then these graphs just reiterate the ability of our system to successfully reduce pressure when compared to the market competitors without the dynamic variable volume system that we have. So for our variable volume design process, again, a variable volume design system is needed because the volume of the residual limb can change so much throughout the day. We are working with the assumption that discounting bruising and other swelling factors, the residual limb will face a steady decrease throughout the day. To test this concept, we needed to show that if the limb shrinks in volume, then you need to add in volume to the liner to basically improve the comfort level. So to do so, we started with our bags at a fraction of our working volume of 120 mil. And then as this figure here shows, we basically added 10 milliliter increments and then performed pressure dynamic testing at each of those stages. So here are some of the examples of our infill tests, including our working volume here of 120. So as we can see from all of these, we pretty much get a characteristic curve that matches this pressure dynamic testing curve we see earlier. So we do get those 10 steps of the limb coming on and off the ground, indicating solid testing. So it's important to note here that we do have some varying sensor contact until we get up to our working volume of 120 mil. This shows our assumption works, that you do need to have a certain amount of volume to be at a comfort level for those sensors to have good contact across the board. Using this concept, we decided to use a one-way valve to continue testing for a variable volume system. This is something we hope to continue in the next few weeks before school gets out. So in conclusion, we were able to develop a successful reduction in pressure for our liner and your functional 5-node haptic feedback system, a variable volume proof of concept, and validated one-way flow. Thank you.